Everybody. Well, this is a talk. Well, you can see clearly that the talk is kind of yeah, runtime, exactly. It says understanding the Go runtime. This is a second part of another talk that I did that was understanding the Go compiler. That is what is behind the runtime there. So it's not, maybe you have seen it, maybe you don't, doesn't matter, it's not needed. We are not going to talk much about the compiler. We have mentioned the compiler and explain a couple of things about the compiler, but that's not the purpose of the talk, so it's not needed. Well, first of all, a bit about me. Well, I'm software engineer at Mattermost. For whoever don't know Mattermost is a open source alternative to Slack that is writing in Go. So if you want to check it out, it's great. But I'm saying this because I want to be clear that I'm not a Go runtime programmer. I'm not a system engineer or something like that. I'm a web developer. I write APIs and TypeScript and React code. So all the things that you are going to see in these talks come from my learning reading through the Go runtime source code. We are going to talk about the Go runtime version 1.21. So everything that you are going to see here, it's going to be about that version. There's going to be some pointers to files and line numbers of the Go runtime code. It's all about that specific version. So if you want to do the homework that I'm going to give to you, you can go to that specific version and search for that specific file and that specific line number. Okay, again, let's talk a bit about the compiler. In my other talk about understanding the Go compiler, I explain in detail how it works, but it can be easily summarized to the next slide. So you have a Go source code that you put somewhere, and there's a magician, that is the Go compiler, that gives you a super fast binary executable. And that's how the compiler works, okay? Well, if you want to know more, you can see the other talk, but it's a good summarization for the things that matters. It's how it works, and it works perfectly. So yeah, that's what the Go compiler does, converting our source code in a super fast executable binary. But that super fast executable binary sounds cool, right? Sounds super amazing. And I want to demonstrate that that can be true, can be not. Let's check it. I'm going to compare Go against C. So how fast is Go? Let's see this example. In this example, we have a package main with an empty main function that is doing nothing, and in main function in C that is doing nothing. So who is faster, doing nothing? Okay, this is the result of the comparison. For doing nothing, Go needs 1.2 megabytes of binary size and 1 second to execute 1,000 times. And C needs 16K and a third of a second to execute 1,000 times. So doing nothing takes 75 times more space in Go and 3 times more execution time. Of course, this competition was rigged up front. So there's no a fair comparison, and the reason is the runtime. C doesn't have a runtime, Go has a runtime. So there's a lot of work done for doing nothing, actually. So, well, the compiler and the runtime is a tandem. They work together to provide you the final result. So the compiler is going to take care of compiling your code, but then it's going to include the runtime in your binary. Okay, that's the case. You have your Go code, you have the runtime, and the linker put everything together, and that's your final Go super fast executable binary. Let's see an example with a hello world. I have a hello world, and this is more or less the result of a hello world. You have this green corner at the top is your code, and this other small block that is the rest of the block, it's the runtime. So The runtime, if your code grows and grows and grows and grows, it's going to keep growing, and the runtime is going to keep the same. So again, it's not a fair comparison, but that's the truth. Most of the binary that you create when you create a hello world is the runtime. And let's see the assembly code generated for my hello world. It's not important to understand the assembly here. That's not what I'm trying to explain. But I want to show you two lines. These two lines here, one is about the FMT println, that is for, it's calling a function that is in a package, normal stuff. But if you see at the bottom, there's something that is calling runtime, more stack, no context. That function there, it's from the runtime. And that is what the compiler does. The compiler, it's whenever it compiles your code, there is some part of the syntax and some part of the code that is compiled to a call to the runtime directly. There's no binary code or assembly code that is generated for every single piece of syntax. There are some parts of the syntax that is generating calls to the runtime. So let's see some examples of that. We are creating here a slice, a map, a channel, and we are looping over the slice and over the map. If we see the assembly code, I remove all the non-calls called for the assembly code, and I reduce that to the call for the runtime. So if you see this line here, I'm appending something to the slice. Because I'm appending something to the slice, and the slice was created with a specific size, what we need to do there is grow the slice. And there it is. The compiler is creating a function call for growing that slice. Also, here we are creating a map. That map is calling fast run for generating the seed of the map that is going to be used for generating the hashes, for distributing the keys inside the map. But well, also is assigning 2 keys to that map. Also, you see that there's another assignment that is generating another function call to the runtime, creating a channel, another runtime call, and sending things is just sending things to a channel, is syntax, but it's generating runtime calls function, runtime functions calls. And whenever you iterate a map, it's also doing map iter init and map iter next. So that's all happening at compile time, is generating all those things because the Go runtime and the Go compiler is a tandem. They work together. So let's talk about the Go runtime. The first thing that is executed when you execute a Go binary, is not your main function. Everybody knows, oh, the first thing, the entry point is your main function. That's not true. The entry point is the runtime, and actually the bootstrap process of the runtime. So this is where you are going to start seeing homework. At the bottom right corner, you are going to see lines, files and lines. That is where I'm talking about certain parts of the bootstrap process, and there is the code where it located. So the first thing, the real entry point of your binary is exactly there in an assembly file specific to your operating system and your architecture. And it's going to, you go there and start calling other things. For example, the first thing that is going to call is thread local storage. It's going to initialize the thread local storage for the current thread to store things in the local thread. The next step is going to be initialize the aux_v, the information that comes from the operating system. Whenever you execute a binary, there is a set of information that is in some stuff that is called aux_v. That aux_v contains these things like the arguments, the environment variables, but also other flags that are provided by the operating system. And the implementation is specific to every operating system. Then we initialize operating system stuff like the number of CPUs, the size of the huge pages, and if you, for example, have SIGO enabled, it's going to adjust certain signal handling. And then it's going to start with the scheduler. The scheduler is a big chunk of the initialization of the runtime because it is initializing the scheduler and other things in the way. The scheduler is going to be from the stop the world that is the next to the start the world that is like 3 lines at the bottom. Everything that is in between that stop the world and start the world is part of the scheduler initialization. But let's talk a bit about the scheduler. What's the scheduler? The scheduler is basically it's the responsible for deciding what goroutine is going to be executed next. There's some pieces of the scheduler that are important to know, like the P is the representation, there's a representation of virtual CPU, the representation of something that is working, something that is executing work. Each processor is going to have a queue of goroutines that are needed to execute. Also, it's going to have normally a goroutine that is running associated to it, and the N is an operating system thread. It's the representation of the real operating system thread that is going to really execute the work in the CPU, because the P is more a virtual concept and the M is more the representation of the thread. And that representation of the thread is associated to the running goroutine also. The scheduler itself also have a couple of lists, have some list. One of them is the list of goroutines that are in the global queue that are going to be executed eventually too. The list of idle Ps and the list of idle Ms. And also there's some global variables that have all the Ps, all the Ms, and all the goroutines. So that's a brief introduction about what you are going to see going on in the runtime all the time. But there's, in the references, there's a talk about the scheduler that is pretty good. So if you want to know more about the scheduler, just take a look to the video in the reference. Well, then is going to be executed as stop the world. Stop the world is something that is common in garbage collectors. It's the pattern is basically stopping everything else and executing everything in serial way. That solves a lot of problem with concurrency and things like that. So it's a common pattern in garbage collection. So the first thing that a scheduler does is stopping the world. Then it's going to initialize the global pool of free stacks. So it's going to generate a certain structures that is going to cache the stacks that are going to be used in the goroutines. So there's a pool of stacks that are there's multiple pools of stack for different sizes, for 2K, 4K, 8K, 16K. Also, it depends on the operating system, but that's the numbers in Linux. And also, it have a cache for bigger stacks. And that, in this point on the initialization, we are only creating the structures, but we are not creating any stacks there. After that, we initialize the memory allocator. The memory allocator is another interesting part of the Go runtime. I'm going to show you some examples here. If you create these slides there that have 124 integers, I can say you that the integers are 8 bytes, and the 8 byte for 124 is basically 8K, okay? 8,192 bytes. So if I do this, if I execute this benchmark, I'm going to get that there's an allocation, and that's the amount of memory consumed. So if I go there and say, okay, I'm going to ask for one integer more, what I will expect is to have 8,200 bytes. That's not the number that is going to be shown there. The number is this one, is 9,472. What? The reason for that is the memory allocator. And I'm going to explain why. This is more or less how the memory allocator is structured. The memory allocator, it's going to, the smaller piece that is important in the memory allocator is the memory pages. That is going to be 8 kilobytes. But the memory is organized in spans. A span is a set of pages. Each span is going to have a specific size. So a specific size for the content. So every single variable that is 8 bytes is going to fall in the span for 8 bytes. Every variable that is 32 bytes is going to fall in the 32 byte span. But that span is not for every single size. So there's some specific size. So there's 8, there's 16 bytes, there's 24 bytes, there's 32 bytes, but and keeps growing and keeps increasing the gap between them up to 32 kilobytes. What happened here is there's a 4K span, but the next span that exists is 9,472 bytes. So in the 4K, it's not enough memory, so we have to store that in the next one. So that's a reason. Also, apart from the spans, there's the mcache that is going to point to all the spans for a processor. There's the mcentral that is going to be a centralized list of all the spans of a specific size for all the processors, and the mheap. The mheap is the one that is going to be responsible of reserving memory, of asking for pages to the operating system. And also is going to take care of anything that is bigger than 32 kilobytes. So let's see another example. Now I'm asking for 8 megabytes, and it's taking 8 megabytes. And then I'm asking for 10 megabytes plus 1 byte. Well, actually, it's not taking 8 megabytes. It's taking 8 megabytes plus 11 bytes. And here, what we have is not, of course, it's not 8 megabytes plus 1. It's 8 megabytes plus 8K plus 11. Because the minimum size of the page is 8K. It's 8K, so it's going to need that from the mheap. So that's how the memory allocator works. Again, this is an oversimplification. In the references, you have a video and an article about the memory allocator. Okay, once we have the memory allocator initialized, we are going to initialize the CPU flags. That is going to take all the CPU-related features that are in the CPU, and is going to assign variables in the runtime to represent what is supported by the CPU. Then it's going to initialize the hashing algorithm. What it's going to do is, if your CPU accepts IS instructions, it's going to take that CPU implementation and it's going to use it right away. If not, it's going to use a code-based implementation of the hashing. Then it's going to initialize the random mechanisms. It's going to initialize the seed also. It's going to create the first structure that represents the operating system thread, and it's going to initialize the ID and all that stuff for that operating system thread, and it's going to add that M to the list of all the M's in the system. Then it's going to initialize the dynamic modules, the modules that are built with shared or plugin mode, and initialize all that stuff and put that in the internal structures. It's going to initialize the arguments. When you get the OS args, what it's doing actually is taking arg slice from the runtime that is exposed using a function and all that stuff. And that is what you are seeing there. That arg slice is initialized using that aux-b that we were talking at the beginning. It's using the same structure that comes from the operating system. Then we do the same with environment variables. The environment variables is going to be a variable in the runtime that is exposed to the syscall package through a function in the runtime, and syscall package is exposing that, and the OS, the operating system is using that syscall package environment method to get the environment variables. Then we have the secure. This is another thing that comes from the AUXV. From the AUXV, you have one flag that is secure execution. That secure execution is telling the program that have to be extra careful with that binary, because that binary can well, can be dangerous in some way. Normally, for example, it's a set UID or set GID binary that is going to be executed with extra privileges, so that it's going to activate that flag, and that flag is going to ensure that the runtime is, if that flag is enabled, is going to ensure that the file descriptor 0, 1, and 2 are defined. If not, it's going to fail, and the go traceback environment variable is set to none. So then it's going to initialize all the debug variables based on the debug compiler option, and on the debug environment variable, it's going to set all the debug configuration in the runtime. Then it's going, well, okay. Well, I know that's a lot of information. I know that it's a bit dense, this talk. I used to do dense talks, so, well, there's a kitten, so that's relaxing always, right? Let's take a big breath, and let's keep going. Okay, the next step is to initialize the garbage collector. At this point, what it's doing actually is to basically configure the pacer of the garbage collector. I'm going to say what is the pacer in a moment. And also is going to say the garbage collector to not sweep anything in the first iteration, because it's not needed. So let me talk about the garbage collector. The garbage collector in the runtime have some different pieces. One is the pacer, another is the garbage collector itself, but there's another three of them, that is the 4GC, sweeper, and scavenger. Okay, let's talk about them. The GC is the one that is going to orchestrate everything. It's going to take care of the mark and sweep phases. It's going to stop the wall, all that stuff that is going to be needed for the garbage collection is going to be done by the GC. But the GC doesn't decide when to run. The one that decides when to run is the pacer. The pacer is it's an algorithm, a mechanism that defines when the garbage collector needs to run. Basically, if you have this GoGC variable that you are passing there a configuration that normally by default is 100, it's you are saying the pacer, hey, I want to get the garbage collector run when we double the memory, when we get 100 of the previous garbage collector cycle memory. And every time the runtime tries to allocate memory, because the program is asking for that, it's going to, well, not every time, but it's going to check if that memory it's already surpassed, that limit's already surpassed, and if it's surpassed, it's going to call the garbage collector to start collecting garbage. Also, there's another thing that is the 4GC. The 4GC is a goroutine that is running in background, waiting for somebody to ask to force the garbage collector, and whenever the 4GC receives a message, it's going to kick the garbage collector. I'm going to tell who sends that message later. The sweeper is a secondary task that takes care of sweeping the unused memory, but the sweeper is an auxiliary task because the garbage collector is going to take care of the sweeping. But if there is some idle time, the sweeper is going to kick in and start sweeping stuff to just take advantage of that idle time. And the scavenger is responsible for freeing memory, freeing pages from the heap. Okay, let's keep going. After this, we create all the processors, all the virtual CPUs that are used for representing well, for representing virtual CPUs in the system. That is going to create a number of P's. Normally, that number is the number of CPUs or the number of cores that you have in your machine. Or if you pass the go max procs variable, it's going to be that number. Also, you can change that on runtime, but that's more or less the idea. And once we have all the P's, we just do the start the world. We start the world again. Now there can be concurrency. There can be they can happen other stuff. After that, we are going to do actually is the last step, that is the initial goroutine. That's the last step in the process, because that is going to be containing everything until it runs your code. That executes a function that is runtime main, and it's and that runtime main is going to start initializing the sysmon. The sysmon is another process that is in the background of your runtime, and is executed every 10 milliseconds. That's not exactly true, because at the beginning executes every 20 microseconds and starts doubling after 1 millisecond up to 10 milliseconds. And when it's 10 milliseconds, it's every 10 milliseconds. But what is the sysmon responsibility? The sysmon responsibility is, have multiple responsibilities. It's going to call the for GC. If there haven't been a GC collection in too much time, it's going to force the garbage collector to have a pass there. It's going to call the scavenger to reclaim memory. It's going to check if the net pool have any goroutine that has already received the information. For whoever don't know, the net pool is a system for having efficient concurrency of I/O in Go. So there's again, in the references, there's a talk about the net pool that is amazing. So just check it. But basically it's for that. Whenever you do a call for example, an HTTP server, that is going to keep up waiting, and the goroutine is going to be paused and put in the net pool. The net pool is going to wait for receiving that information, and when the net pool receives that information, it's going to mark the goroutine as ready. And this is one of the ways that the goroutines get marked as ready, through the sysmon. Also, the sysmon is going to preempt long-running goroutines. If there's a goroutine that has been running for too much time, it's going to send a signal to preempt that. And it's going to check if there is something that is executing what is called a slow syscall. A slow syscall is a syscall that is taking too much time, and that means that you can deassociate the goroutine from the processor and let the operating system thread to deal with that execution, and use another operating system thread to execute another goroutine. But yeah, that's it. And also take care of some scheduler traces. After that, it's going to initialize it's going to enable the garbage collector. Enabling the garbage collector means that it's going to call the sweeper and the scavenger, and it's going to mark the garbage collector as enabled. That means that since that point, the garbage collector can start running cycles of garbage collection. After that, it's going to run all the init functions of all the packages that are in your binary. And finally, it's going to run your main function, and in consequence, your code. So that's everything that happens just before it's calling your main function. So now, if you see in perspective the comparison with C, doesn't sound like that bad, right? Okay, let's talk about what happened during the runtime. Okay, your binary is already running. What is going on under the hood? Well, there's a lot of things going on. There's the garbage collection with the sweeper, the force.gc, all that stuff going on. This is there's the scheduler taking care of a rescheduling goroutine with the P's and the M's and all that stuff. It's the net pool also taking care of that goroutines that are doing I/O. For sure, it's the P's and the M's, and it's the sysmon checking every 10 milliseconds if everything is going well. Also, during the runtime, your code is going to call the runtime for doing normal actions like spawning goroutines, allocating memory, doing operations with maps, channels, whatever. So that's it. That's the Go runtime. I'm going to give a quick summary. Again, let's go quickly over all these. Thread local storage, then the args from the argv, then the operating system with the number of CPUs, all that stuff. Then the scheduler that is going to be stop the world, get all the goroutine stacks pool, the memory allocator for storing memory, the CPU flags for knowing what is supporting the CPU, the hash algorithm with IS, the random generation, the main thread, the modules that are in your package, the Go arguments, the Go environment variables, and the secure, if you have that flag in the AUXV, the debug environment. Then we start initializing the garbage collector, but we are just configuring the pacer, create all the P's, start the world, and we start running the first Go routine. With the first Go routine, we start the sysmon, we start the scavenger and the sweeper from the garbage collector, and we enable the garbage collector. We run all the init functions, and we run your code. So that's how it works. And also remember that a lot of the stuff that is going on, it's just written by the compiler to say, hey, run this in the runtime. Another thing that I want to share is all the illustrations of this talk are made by Juan de la Cruz. They are Creative Commons Zero, so they are public domain. So they are mine, but they are yours too. So you can do whatever you want with them. You don't need permission for anything. So you can do t-shirts, you can do stickers, you can do whatever you want. Or do your own presentation with them. They are in penpot format, that is an open source alternative to Figma, and you can download there in that URL. Also, I have a gift from Mattermost. My company makes some pins and stickers and all that stuff. So if after the talk you want to get some nice stickers, nice pins of very nice gophers, just come here and take them. If you don't want them, but you want to ask me something and you don't want to ask during the questions and answers, come here, take a sticker, ask me whatever you want, and then throw up the sticker. That doesn't matter. Yeah, it's an excuse to approach me, so that's perfectly fine. Some references. Again, there's a lot of cool stuff out there. My presentation is a very shallow presentation. I want you to get general vision of the runtime and why it's there and what it does. But if you want to get into the details, there's a lot of cool stuff out there. There is a very interesting talk from Maya Roscranes, I think was in the GopherCon Israel. So there's a very good talk, a very good article about the memory allocator, a very good talk from Mahat Jibrajani about the GC Pacer. There's another one from Mahat Jibrajani about the scheduler. Both are amazing. Very, very, very detailed and very deep, but they are amazing. The memory allocator by Andre Carvalho, and another one about the net pool that is super interesting too. And if you like this talk, I have a couple of them that are kind of related. The one is the understanding the Go compiler in the GopherCon UK, so you can check it there. Also one about goroutines in the London Gophers meetup, that is the secret life of a goroutine, that explains more or less how the scheduler works, but from the perspective of a goroutine. And that's it. Well, I know that's a very dense topic. It's a very a bit hard to follow, it exhausting. But the real thing that I want to transmit here, or to convey here, is I remember that I just remembering that I'm a web developer. So I did that by reading the source code of the Go runtime. That means that the source code of the Go runtime have to have certain characteristics that allows me to do that. And one of them is it's Go, so it's kind of familiar place to be, and also it's very well written, and it's very well documented. If you go to the code, I'm not going to say it's easy to understand, because at the end of the day, it's a production runtime for a programming language, but it's something that you can explore and you can learn from it. So I want to encourage you all to get there and explore the source code of Go, and try to learn something like this, because all that aha moments, all that clicks in your head, that's magic. So thank you.
Questions?
Do you have any suggestion related to, for example, investigating memory leaks or issues like enable pprof and investigating how the runtime is interacting within your code or application?
Sorry, it was hard for me to understand.
Yeah, so basically, maybe it's much better like this. Since now you are probably a runtime expert.
No, I'm a web developer.
Exactly. So when you basically have to investigate around some memory leaks or issues of those kind of problems related to memories and such, you maybe have to enable pprof and investigate in the profile and such. Do you have any suggestion about what to look for, how to interact with the profile, and what to see maybe from the runtime that can help you about it?
Well, not really. I don't have any advice there, because it's not my area of specialty. So I'm not an expert on that. So what I will say is understanding how the memory allocator works and understanding how the garbage collector works can help you understand better where a memory leak is. But yeah, at the end of the day, you have to use the profiler, you have to use the debugger, and you have to find that. And finding memory leaks is something that is kind of challenging. So, and again, I'm not an expert on that, so I can't answer that question.
What are the differences between in the initialization process between different architectures on different platforms like mobile, ARM v8, x86?
Yeah, well, I did all my investigation on Linux because it's what I'm using, but there's the Go compiler is writing in two main languages actually. It's writing in Go, of course, and it's writing in a pseudo assembly or assembly that is it's specific for the architecture. So for example, whenever you initialize, whenever you start running the Go binary, the first thing that it's going to do is use a completely different entry point depending on your architecture and your system. And that entry point is architecture specific and it's writing in assembly. And there's the first step of the initialization of the bootstrap of the Go runtime. It's basically assembly. There are some parts that are using assembly. For example, whenever you, if I recall correctly, whenever you check if the IS algorithm is supported by the CPU that is writing a small function in assembly and is called from the Go code in the runtime. So there are some parts that are architecture specific, and if you go to the source code of the Go runtime, you're going to see a lot of .s files that are specific for the architecture and the CPU and maybe the operating system. And that is the ones that are going to be specific to that. But there's some things that are clearly at the beginning, and there's some things here and there, small things here and there. I think, for example, the memory locator, I think there's have some things that are also done in assembly. I think some primitives related to concurrency and all that stuff. I think that's also made in assembly. So I'm not 100% sure of all the cases, but yeah, that's that. I don't know if that answered your question. Okay, thank you.
Yeah, I would basically have a question up to the entire, basically for the entire runtime initialization up to the main thread. Since the runtime in and of itself is part of the binary, the exec call for the kernel would already need to schedule it, and there would have to be a mapped kernel thread in order for the runtime to be executed in the first place, hence being able to initialize. And where does the main thread from the runtime in that fit in that picture?
Can you repeat the question, please? I didn't follow everything.
You do an exec for your binary. In order for your binary to be executed at all, it has to create a thread. That kernel thread has to be scheduled by the kernel to a processor in order to run in the very first place. Since the entire runtime is part of the binary, where does the runtime get the ability to basically set the main thread, because that was pretty way down in the second line?
Okay, how the runtime take care of the threads of the operating system?
Yeah, because the main thread already would have to be initialized and scheduled in order for the runtime to be able to do anything in the first place, because the runtime wouldn't run.
Yeah. Okay, the main thread, whenever you have the main thread, that is the one that is going to execute everything at the beginning, okay? And then what you have is every time you need a thread, because it's needed because you have enough goroutines to need a thread, and the number of CPUs, it's not all the virtual CPUs are not used yet. So if you have all the CPUs used, you are not going to spawn any new threads. But if you don't have all the CPUs used yet, whenever a goroutine comes and say, hey, I need to execute, it's going to take one of the idle threads, or if there's not idle thread, that it will be the case at the beginning, it's going to spawn a new thread, initialize the thread information, only the thread information, not all the bootstrap process, only the thread information, and start executing the code for that goroutine. And whenever it finishes, it's going to move that to idle again, or take another goroutine, or something like that. So that's more or less the idea. I don't know if that answered your question or not.
Okay, so basically the main thread for the application in the very end is managing the thread pool for the goroutines.
Okay, you mentioned Sigo, right? I'm not.
Not Sigo, not
Okay.
Sigo.
Oh no, for your Go. Okay, here's the main thread. I don't think there's any difference between the main thread and the rest of the threads. The main thread is going to start executing the first goroutine, and then it's going to do. It's going to start. Pausing. Well, the thread is going to be one of the threads that is going to be executing things. So there's no difference between, in my opinion, I'm not 100% sure, but I think there's no difference between the first thread and the thread number 7 or something like that. It's going to start executing things, and it's going to start scheduling goroutines, and it's going to start adding work there. So it's not special. It's the first one because the first one was there at the beginning. That's it. That's what I think. But again, I'm a web developer. I'm not 100% sure of that specific implementation detail.
Yeah, but the main point there is if the main thread ends, as in the map kernel thread, that spawns the other threads, the kernel will kill the entire process.
Yeah, but then probably the main thread is just flagged as is the main thread, and it's not going to finish that. But it's not going to do anything special, I guess. I will expect that thread to behave like any other thread in the Go runtime. That's what I will expect. Maybe I'm completely wrong.
Well, I might have missed that part because, as you said, the talk was very dense. But I didn't see anything about channels. And when I was learning Go, I read that channels cover a lot of complexity to make easy to communicate between goroutines. And I'm wondering, is it really that complex reading through the runtime code, or maybe they just don't require anything special in terms of initialization?
Okay, I like that you asked me that question because there's a lightning talk tomorrow about how the channels work internally. The channels is just a data structure. It's a data structure that have certain logs, that have certain buffers and certain lists and things like that. So there's nothing super special about channels. So the runtime doesn't need to do anything special about channels. What it does is using certain functions that are in the runtime whenever you found the syntax about goroutines. So whenever you see a go call, it's going to call the new prop for generating a new goroutine. Whenever you see a send, it's going to execute chance send to the channel, all that stuff. But at the end of the day, it's a data structure. And I love that you asked that question because that's one thing that you can go there and explore in the Go runtime. You can see the code, but if you want to explore it, just come tomorrow to my lightning talk. So I'm spamming a lot today, so my talks from the references are now this. Okay, so any other question? Yep, over there.
So I would be interested to know why you started to look into the runtime. So did you hunt some bugs, or was it just curiosity?
Yeah, well, it's about curiosity. I did previously the understanding the Go compiler talk, and was about curiosity. It was something that I want to learn. I did want to understand how it works because it's one of the tools that I use every single day. And the Go runtime was kind of the next step, the obvious next step. Okay, I understand more or less how the compiler works in a shallow overview. I want to have a shallow vision about how the runtime works. So I start investigating that and I start digging into that. There's nothing else about except curiosity. I did want to learn about that. That's it.
Okay, ciao, great talk. So I have a very small question. In the last part, there is the init part where you initialize the function, the init functions. Okay. Yeah. But if there is one single function, say in the main, then it's clear to me what is happening. But what happens in, say, we have a main with an init function, multiple packages with an init function. I assume they cannot be run concurrently. So what is the order?
What is going to happen is that they are going to execute serially, and they have a specific order. Actually, I love, now I'm going to spam but about other talk that is not mine, I promise. There's tomorrow, I think is from David Marty, a talk about exactly that. Well, it's not exactly that, but it's talking about what happened whenever you run your binary, but it's kind of from the after the bootstrap process, all the initialization of the functions, what is the order, what's the packages, if multiple packages have that. But yeah, there's a specific order and it's going to execute serially at the, well, in theory, I don't know if you can execute a go call. I guess you can execute a go call in an init function, but that will make that concurrent. But at the beginning, it's upfront, it's not concurrent. It's going to execute in certain order, and it's going to execute one after another.
Thank you.
Any other question? Okay.
Thank you, Jesus.